These are the results of our work that we have done in set. Now we are live on YouTube. These are results of our work that we have done in the previous 5 years with my advisor, Dr. Marshall Longla. And I'm going to present exactly the way Mouse, can you help me? Can you help me? Check correctly. It's not passing out. Okay. So yeah, I'm going to present it just the way it appears in my dissertation. My dissertation has 5 chapters. We have an introduction, then we have chapter 2, perturbation of copulae, whereby we studied perturbation of copulae by addition of a factor term and another method of perturbation, which involves addition of some random noise to the underlying random variables. Then after that, we studied the effects of these perturbations on measures of dependence. Chapter 3, we studied copulae, perturbations, and mixing. Then in chapter 4, we studied or we compared continuous versus discrete state space Markov chains to see that to bring out a difference between continuous and discrete state Markov chains. Then we'll do a simulation study of the 4th chapter and bring conclusions for all the entire work. But first, before let's look at why should one study copulae? Why should one be interested to study copulae? Where are they applied, or why are they important? So copulae are useful in representing the joint distributions of random variables, enabling the examination and detection of possible correlations between random variables. Among the primary applications of is their use in modeling temporal dependence within Markov processes. And a copula-based Markov chain is a stationary Markov chain generated by a copula of its consecutive states and an invariant distribution. They were first studied by Dasso and others in 1992. And since then, they have gained a lot of popularity in modeling dependence across various fields, including technology, finance, economics, healthcare, hydrology, and many others. In application, identifying a suitable copula is very important. Copula that fits the real data. And this involves exploring various parametric families. After selecting the copula, our focus shifts towards finding a slight perturbation on C that better fits the data compared to C itself. And this process in the last slide is what we call perturbation of copulae. But what's a copula then? According to Nelson 2006 and other definitions before then, a two-copula is a bivariate function defined with the domain on the unit square and taking values on the unit interval and satisfies the following properties. If any of the variables take the value 1, then the value of the copula 0, then the value of the copula will be 0. If any of the random variables take the value 1, then the value of the copula will take the value of the other random variable, which is not 1. Then it satisfies the two increasing property. The applicability of copulas in distributions was brought up by a theorem in Scalar 1959, where he gave the relationship between the joint distribution of random variables and copulas. And the theorem states, let X and Y be random variables with joint cumulative distribution function H and margins F1 and F2 respectively. Then the function C defined by equation 1 is the copula of the random vector X and Y. If the random variables are continuous, then C is unique. Otherwise, C will be uniquely defined on the product of the range of F1 and the range of F2. We gave some three examples of copulas that are important in this work. And these include the independence copula. If the random variables X and Y are independent, then their copula will be P, the first one, which is called the independence copula. Then we have the Frechet-Hookedean upper bound copula, denoted by M, and the Frechet-Hookedean lower bound copula, denoted by W. These are important in our work. Also, in application of copulars, there are some important operations on copulars that we need to understand, and these include the Ford product of copulars. Given two copulars, copular 1, C1 and C2, their Ford product is defined by equation 2 as an integral. Then we have an important extension of that, the N-Ford product. The N-Ford product of N copulars, is defined recursively by equation number 3. Then another important aspect of operation on copulars is the convex combination of copulars. If C1 to CK are copulars, then the copular defined by equation number 4 is called the convex combination of the copulars C1 to CK. AJs must be, the coefficients must be between 0 and 1, and their sum must be 1. Some important families of copulars which we used in this work include the Frigid family of copulars, which is a comprehensive family of copulars. We can see that, interestingly, if A and B are equal to 0, this copular will simply be the independence copular. And if A is equal to 1, we have complete dependence because the other part becomes 0. So this copular is interesting, and we will use it in chapter 4. Then on the same copular, if A plus B is equal to theta squared, we obtain what we call the Maglia family of copulars, which is closely related to the Frigid family of copulars. Our work involves applications of copulars on Markov processes. So we want to define what's a Markov process. A random process, xt, is said to be a Markov process if for every finite subset, T naught to Tn of T, and T in T, such that they are ordered in that way, then they satisfy this property, which is called the Markov property. That means that the next step taken by the process does not depend on the past, it depends on the current state. That is the Markov property. What about copular-based Markov chains? In the second slide, we just say that copular-based Markov chains are Markov chains defined by the copula of their consecutive states and an invariant distribution. So given a Markov process and an invariant marginal distribution for the random variables in the process, we can define the copula for the process as given in equation number 8. And this is called the theorem we have seen behind, which is the Scalar's theorem. Once you have that, the transition distributions of the process are given by taking the derivative of the copula with respect to the first random variable. And we can generally represent the Markov chain using the N-Ford product of the copulars. So generally, if X has a copula C, if the Markov chain has a copula C, for consecutive random variables, then the copula of XSXR is represented in this way as a Ford product. In other words, we can represent it as the R minus S Ford product of C. This brings us to the end of the introduction. And now we are going to what we did in this dissertation. We are going to begin with perturbation of copulars, but before we do that, let's define some useful results which we came up with in this work that helped us prove results in this chapter. We show that if Cn is a sequence of complex numbers that converge to C, for alpha between 0 and 1, if we define An by the sum given in 11, then as n approaches infinity, this sum will also converge to C. Prove that. Then another important result which we apply to make proofs is a lemma on commuting copulars. Let C1 and C2 be two copulars that commute, then this the N-Ford product satisfy, or the N-Ford product of this convex combination of the two copulars is simply the binomial formula. That's important in making proofs, but then what are perturbations? The first form of perturbation that we considered was a perturbation that adds a factor term to an existing copula. So this class comprises of perturbation of the form 11, and we came up with this theorem. We have this theorem. Let C and C1 be bivariate copulars, and alpha be a real number between 0 and 1. Define the factor term H alpha as given in equation 14. Then the function C alpha given by equation 15 is a copular, and this is a perturbation copular. In this study, to understand the behavior of these copulars, we gave two examples, and we used these two examples to study the long-run effect of the perturbations of this form. So if the copular C1 is the independent copular, the perturbation takes this form. If the copular C1 is M, then the perturbation takes this form here. We want to understand the long-run behavior of these perturbations. So the long-run behavior of these perturbations, we chose to study using the nth-fold product. So if we take the nth-fold product of the copular 16, the nth-fold product of that copular looks like that. And the nth-fold product of the other copular 17, the perturbation 17, looks like equation number 19. The proof makes use of I can give you this. I printed the results there. The proof makes use of the previous result you have seen behind. And this proof of the second one still makes use of that. For any alpha between 0 and 1, if the limit of the nth-fold product of the perturbed copula converges to C0, then the limit of the perturbation that uses M converges to C0. But you can see that the perturbation that uses the independent copula completely transforms the original copula so that it converges to the independent copula. So we'll see that in other results ahead. The other form of perturbation, we will show what are the effects of these perturbations on measures of dependence. The other form of perturbation we studied was perturbation of copulars under noise. What happens here is that we add some random noise to the underlying random variables, X and Y. And the first form we studied was adding random noise to X alone. What kind of a copular results from that? And the other form, what if we add random noises to both Y and Z? This study needs us to understand the distribution of X and Z. The distribution of X plus Z and X plus Y. So to understand or to study this, we used the uniform distribution. So suppose X and Z are identically independent identically distributed random variables with uniform 0-1 distribution, then the distribution of X plus Z is given by equation number 20. This distribution is called the Irwin-Hall distribution, and it was first studied by Irwin and Hall in 1961 and 1960 respectively. We get the proof. Now, let X, Y, and Z be such that the random vector of X and Y has a copular C and joint distribution function H. Assume that X, Y, and Z have respectively cumulative distribution functions F1, F2, and F3. Moreover, assume that Z is independent of X and Y. Then the copular of X plus Z, Y, of the random vector that is found by equation 21, where F4 is the distribution of X plus Z, and that is the quasi-inverse function. When we perturb, and we gave examples. So the first example shows that the independence copula is not affected by this form of perturbation, because if X and Y are independent, then their copula is the independence copula. And if X and Y are independent and Z is independent of X and Y, then this is also independent of that. And again, the copula of that remains to be that. But when the X and Y have copula M, there will be a change. The resulting copula or the perturbation will take this form here. We showed that. What about when we perturb or when we add some random noise to both X and Y? let x, y, and z be such that x and y, the random vector x and y have a copular C and joint distribution function H. Assume that x, y, and z have respective cumulative distribution functions f1, f2, and f3. Moreover, assume that z is independent of the random vector of x and y. Then the copula of x plus z, y plus z is found by this formula here, where f4 has been defined previously, and f5 is the CDF of x, y plus z, and that is the quasi-inverse function defined that way. When we use the independence copula in this case, when the independence copula is used, is the copula of the random vector x and z, there is a change in this form of perturbation, because when the original copula, the copula of x and y is the independence copula, then the perturbation looks like that. We have the proof shown in the dissertation. Can you distribute that? Then we have the perturbation given by this formula, all of that. It's given by that formula. Yeah. If x and y have the distribution function m, then the copula of x plus z remains to be m, which remains unchanged. What are the effects of this mesh? What are the effects of these perturbations on measures of association? So we studied the effects of this perturbation on the Spearman's rho, Blomqvist beta, and genus gamma. And we showed that if we perturb the original copula C using M, then the effect of that perturbation on the copula C is evident there. And it depends on the size of alpha. But when we use, for the perturbation using alpha, using the independence copula, the perturbation rescales the Spearman's rho by a factor 1 minus alpha. And also for the genus gamma, the perturbation rescales the genus gamma, and the perturbation also rescales the Blomqvist beta. So the perturbations using the independence copula is evident here. It reduces the dependence in all cases. But the one using M has effects, but may not declare whether it's reduced or not. Then we also studied the effects of these on mixing coefficients. These are the mixing coefficients that we used in this one. And why are mixing coefficients? Allow me to take 2 seconds to explain that. What are mixing coefficients and why are they important? So once we understand the mixing coefficients of a sequence, we can state the central limit theorems of the sequences, and from there we are able to estimate parameters in the model and also do inferences. So once we know mixing properties, we can do those things. We can estimate and also do inference once we know the central limit theorems. So we show that let xt be a stationary Markov chain generated by the perturbation that uses the independence copula given in 16 and an absolutely continuous marginal distribution F. The X is low psi mixing. Yeah, and the proof of this uses some results from Longler 2015, whereby Longler stated that any convex combination of copulas that contain the independence copula has density of its absolutely continuous part bounded away from 0. In our case, this is a convex combination and it contains the independence copula. So its density, according to Longler 2015, is bounded away from 0. Then in the same paper, I show that if for some positive integer n, the copula of the random variables x0, xn as an absolutely continuous component with density bounded away from 0 on a set of Lebesgue measure 1, then the Markov chain will be low psi mixing. So the proof follows directly from that. What about the effects of these perturbations on beta mixing? Any perturbation of a copula of the form that uses pi generate beta mixing Markov chains with exponential mixing rates. Any perturbation of the copula that uses M also generates beta mixing if the original copula generates beta mixing. And we provided the proof for that, which makes use of the results we have on the first page of the first paper provided. And easy to show. When a copula is perturbed using the independence copula, the alpha mixing rate of convergence is multiplied by an exponential factor. For a perturbation that uses the copula M, if the initial copula generates alpha mixing Markov chains, then the perturbation will also generate alpha mixing. But if the original copula did not generate alpha mixing, then even the perturbation does not generate alpha mixing Markov chains. What are the effects on pi mixing and psi mixing? Let's see the copula. For the perturbation that uses the independence copula, the following odds. The pi mixing converges to C as n goes to infinity, then the perturbation that uses M is the same. But for the perturbation that uses the independence copula, then there's psi mixing. I didn't mention that psi mixing, a random process is said to be pi mixing if phi n tends to 0 as n goes to infinity. It's also beta mixing if beta n goes to 0 as n goes to infinity. This is why I've been talking of mixing and showing that. So that means it's psi mixing, it's pi mixing. Perturbations by means of the independence copula increases the convergence rate exponentially. But perturbations by the use of M in the examples provided are never mixing. So in summary, we can say that perturbations that make use of the independence copula transforms non-mixing Markov chains, mixing Markov chains. And we can have several limit theorems for the associated sums of random variables. Yeah, this brings us to the end of chapter 2. Yeah, and now on to, that is chapter 3 on mixing. On to chapter 4, we did a comparison of continuous versus discrete state space Markov chains. And what we did here is that in Longer 2015, he showed that if you can look at this copula here, it is from the Frigid family of copulas. But in this case, F plus B is equal to 1. So I wanted to understand, Longlast in 2015 showed that Markov chains generated by any copula from the Frigid family are never pi mixing. I wanted to study what if the marginals are discrete. And I considered Bernoulli marginals. We considered Bernoulli marginals to do this study. He also showed that when A plus B is equal to 1, which we have in this case, then strictly continuous Markov chains generated will not be mixing at all. So we considered Bernoulli marginals, which are discrete marginals, to do this study. But before we do that, Longler 2014 showed that if the marginals are uniform 0, 1, then the stationary Markov chain generated by the copula 23 will have n steps joint cumulative distribution functions of the form of this one. If the marginals are Bernoulli P, we show that the joint distribution functions can be characterized by the transition probabilities, because we are dealing with a discrete state space Markov chain. So if let X be a stationary Markov chain generated by the copula we have seen behind, that is from the Frigid family, A plus B is equal to 1, and Bernoulli P marginals, then this Markov chain has transition matrices given by 24 and 25. The transition matrices split into 2 depending on the value of P. And we provided the proof of this. It is sufficient because the Markov chain is stationary. Oh, sorry. Because the Markov chain is stationary, it is sufficient to just show the probability x0 equal to 0 and x1 is equal to 0, then fill out the rest of the gaps there. So we showed that probability, this one, applying the scalar theorem in this step, and using our copula above, we can simplify the distribution to that form, which splits p less than half or p greater or equal to 1/2. The rest of the probabilities in this distribution table are filled out because we know the distribution, that one, it's not 0, and the distribution of x0 is equal to 1. We can fill out the rest and proceed to find the transition probabilities using the definition of conditional probability. That is, we define each of them is here by that. And we obtain the transition matrices on the previous slide. This is important in finding the mixing properties of this Markov chain. It's important that it's the end transition matrices for the transition matrices 24 and 25 are respectively given by equation by 26 and 27. The end transition matrices give us the probabilities of moving from x0 to xn. So that's important. And this can easily give us the distribution of x0 to xn. That's why it is presented here. So we want to use that information to study the mixing properties of the Markov chain generated by our copula. And the mixing properties we study here is especially these mixing properties, property, the psi mixing. That is the mixing property we will derive. So for random variables, n steps apart, such that x0 belongs to A and xn belongs to B, we define these two mixing coefficients. A stochastic process is said to be psi mixing if psi n goes to 0, as n goes to infinity, and pi mixing if pi n goes to 0, as n goes to infinity. We showed that if X is a stationary Markov chain generated by our copula from the Pritchett family and Bernoulli P marginals, then X is exponentially psi mixing. Psi mixing implies pi mixing, rho mixing, beta mixing, and alpha mixing. And the proof makes use of the end transition matrices we have seen above. So for p less than 1/2, the joint distribution of x0 and xn is obtained from the end transition matrices we have seen in the previous slide, and it will be like this. That would be the end transition matrix. This will be the distribution, and from this distribution, we can compute these values. Which are the values we have in the psi mixing coefficient? We can compute these values. Then, because the psi mixing coefficient is the supremum of these values, then we take the supremum, and the supremum shows to be that one. This value for p less than 1/2 and any a will be less than 1. So as n tends to infinity, this goes to 0. And this Markov chain is psi mixing Markov chain. So when we use discrete marginals, we actually have mixing. Once you know mixing properties of a Markov chain, we can derive central limit theorems, we can do estimation, and we can do inferences for the parameters within the model. So in our case, we went ahead to do estimation using the MLE. When p is less than 1/2, the likelihood function for the Markov chain is given by equation 31. Finding the log likelihood and solving for A, we get an expression for A in the form 32. Then P can be solved from solving this equation, which is a bit complicated, whereby, did I mention that? Whereby the Nij denotes the number of times I is followed by J. When we talk of Bernoulli trials take two values, 0, 1, for instance. So this is not easy to solve by hand, but we used hand to find the MLEs of A and B, which will be shown soon in the simulation study. The following conditions, however, need to be satisfied for us to make use of that, how to find the MLEs. These conditions were stated in Billingsley 1961, and they say that condition 1, for any theta in R2 in this case, then theta is in the transition probabilities, which are functions of theta being greater than 0, is independent of theta for each transition probability, and they have continuous derivatives up to the second order. Then we also need that the 4×2 transition matrix in this case, which is a simple case, this transition matrix must have a rank of 2 for us to obtain MLEs and asymptotic normalities. Then for each theta, there is only one ergodic state in that Markov chain. In our case, those properties were satisfied, and we showed that actually, for our Markov chain generated by the copula from the Frege family with A plus and Bernoulli P marginals, then we can have MLEs. There exists an MLE, and that MLE satisfies this asymptotic normality property with variance-covariance matrix given by equation number 34. The proof of this theorem follows by verifying these conditions, condition 1, condition 2, and 3 in the previous slide. And the variance-covariance matrix is the inverse of the information matrix obtained this way. We have provided that proof in the dissertation, and takes a few pages to prove it. P can be estimated by several different ways. One way to estimate P is the MLE, as you have seen. Another way to estimate P is the sample mean, because the Markov chain happens to be stationary. And the other way is a robust estimator proposed by Longard 2021 and Benitez, and we will use that later in simulation. But what's important here again is that if we have a stationary Markov chain generated by the copula we have in this fourth part, then the sample mean P bar has an asymptotic normality of this form. The variance was derived. It's derived in the dissertation, and we don't provide the proof of this theorem here. But this theorem now makes use of a theorem by Ibragimov and Linik, 1975, which is a theorem on psi-mixing Markov chains. And that makes it, for us, easier to make our conclusion. And now we can go ahead and do confidence intervals for P bar. If Xt is a stationary Markov chain generated by our copula and Bernoulli P marginals, we wanted to understand, is there independence in this model? Because sometimes you can have a Markov, you can have a sequence, which is actually a sequence of independent random variables. We wanted to understand, when is there independence in this Markov, in this sequence? Is it actually a Markov chain? So we did a study for that, and we showed that we did an hypothesis test for that, and we showed that for our Markov chain generated by the copula 23 and Bernoulli P marginal distributions, then X naught, the sequence is independent when A is equal to P, for P less than 1/2, and for P greater than 1/2, it's independent when A is equal to 1 minus P. To do that, we have to do a test. We made the proof, but we have to verify using a test, an hypothesis test for independence. So for P less than 1/2, we consider the likelihood ratio test. Different methods have been proposed: the chi-square test for the frequencies, the likelihood ratio test for the MLEs, and we consider the likelihood ratio test, which is in literature. And this is the likelihood ratio function, which looks like that. The decision rule is to reject H0 in favor of H1 if -2 log lambda 1 is greater or equal to chi-square 1. Significance network. The test for P greater or equal to 1/2 has a similar derivation, and we don't provide that here. So this is our simulation study. We used R to obtain the estimators of A and P. And we obtained estimators which were very close to the true value. These are the true values used to generate the Markov our Markov chain. And we generated Markov chains of sizes 499, 500, 1,000, and 5,000. Because the chains are of length n+1. Then we estimated our parameters. But the estimates are not exactly provided here because we replicated our Markov chains 400 times to construct 400 confidence intervals. So in this case, we have 400 estimators for A, 400 estimators for P, and it's not good to just choose one. There is no good way to choose just one of these 400 estimators. So our results, which are provided here, are the constructed confidence interval lengths for A and P and the coverage probabilities. We want to see, are these coverage probabilities close to the confidence level of 95? So in our simulation study, we realized that the confidence interval mean length for A, as P increases, the confidence interval mean length for A decrease. This is because the variance of the estimator family of A depends on P, and it decreases as P increases. That's the reason why you can see this. For any increasing P, we have this confidence interval mean length increasing, and the result repeats everywhere. We have repetition of that. Interestingly, as I said before, the estimates observed for the parameters were very close to the true values, but we didn't include them because we have 400 of them. Again, for the coverage probabilities for A and P, these are very close. They become close as the sample size increase. So actually the estimation is affected by the size of the samples. So the coverage probabilities, how many times does the interval contain the true value? These proportions become almost accurate, not accurate, but not very correct, but very close to 95% as the sample size increase. For P greater or equal to 1/2, we show the same. Then we did a simulation study to understand what kind of a sequence do we have. And in our simulation study, using the likelihood ratio test, we realized that actually our sequence has independence when A is equal to P. When A is equal to P, our sequence is no longer a Markov chain, but it turns to a sequence of independent Bernoulli triangles. Yeah. That is for P less than 1/2. But for P greater than 1/2, we realize that our sequence is a sequence of independent Bernoulli triangles when A is equal to 1 minus P. So you can see that. And for the rest, it's a Markov chain with Markovian dependence. We mentioned that there are several estimators for P. The MLE of P, the sample mean, and a robust estimator for P. So we bring in here the estimator proposed by Longland Belligrad 2021, which is called a robust estimator. A robust estimator is an estimator that remains unaffected by outliers and other factors. So this is the robust estimator proposed by Longland and Belligrad 2021. And HN is the optimal bandwidth, and XT in this case is actually a sample from our model. And YT is an independently generated sample following a standard normal distribution. A 1 minus alpha times 100% confidence interval for the robust estimator is given like that. And we compared 3 estimators for P and saw that the MLE is the best estimator for P. The sample mean follows the MLE very closely. It's a good estimator, but it's not as good as the MLE. the robust estimator becomes accurate for large sample sizes, for some sizes 5,000 and greater. So all estimators actually are asymptotically equivalent. They all, and again, we didn't provide the actual estimators for the actual estimators because, again, we replicated the Markov chains 400 times. So we had 400 estimators, which we can't choose just one to include here. So this comparison is done based on confidence interval mean lengths. And confidence interval mean lengths, the narrower the confidence interval, then the more precise the estimation. That's the point. And we can see that this is not really, the first was not really very accurate, but we can see that for P hat, the confidence interval mean length is very narrow compared to the rest. So P hat or the MLE of P happen to be the best estimate here. The coverage probabilities improve as the sample size increase. So we have better coverage probabilities with bigger samples. And although the robust estimator does not beat the other two, it becomes an efficient estimator for samples. It becomes an accurate estimator for samples greater or equal to 5,000. So these three estimators are asymptotically equivalent and they provide very precise estimations for our case. The same situation happens for P greater or equal to 1/2. We obtain the same results as explained previous slide. And these were some, not everything, but some of the main observations conclusions that we made from this work. But when dealing with Markov chains in the Coppola framework, the work with mixing coefficient benefit from the fold product. And this makes it easier for us because as compared to the general case. So using fold products is a handy way to get an easy approach. Along Markov chains generated by perturbation copulas, the copulas remain in the class of the given perturbations when the independence copula is used. A perturbation of a copula using the independence copula always transforms non-mixing. In this case, we mentioned only beta mixing. Rescales the beta mixing coefficient and increases the rate of convergence exponentially. That is, it converts non-mixing sequences to geometrically ergodic. Geometrically ergodic means the beta mixing coefficient converges exponentially fast. Marginal distributions affect the mixing properties of copula-based Markov chains. We have seen that, and this is the main result for chapter 4, or for the last chapter, because it gives us the difference between continuous state space Markov chains and discrete state Markov chains. For Markov chains, based on the Pritchett and Muia families, it has been shown previously that there is no mixing when A plus B is equal to 1. But in our case, we have shown that these copula generate mixing when discrete marginals are used. And therefore, we can have central limit theorems established for model parameters. These are actually not our conclusions for the entire dissertation. We have more conclusions inside there. And my committee, as you can see, we have more conclusions there. That's not the conclusion for 5 years, just what you can have in the slide, on the slide. These are some of the references used in this work, just some. The most important mentioned on the slides. And I would like to thank my advisor, Dr. Marshall Longla, for his tremendous help in coming up with this work and his comments and his critics on the mistakes I made. I was not the same when I joined 5 years ago, but I feel like I'm different. I would also like to appreciate my committee members, Dr. Spiro, for always making suggestions like instead of telling us to give time, you can use a Google poll so that the committee can vote which works effectively, and other ways you have helped me through. Dr. Izin, Dr. Dan, and Dr. San for their tremendous help in improving my work. And also my friends, that is Dr. Shields and my friend, Mr. Davis and Dr. Nathan from the Department of Engineering. Thank you so much for all your help through this work. And to my fellow, and Dr. Vinovich, I'm sorry, and Dr. Clark. Sorry, I didn't forget. Yeah, thank you so much for your input in this work. And to my fellow students, thank you so much for your critics on the laughs we have and the comments we made on my presentations a few days ago, which made them better. Last time I presented in 1 hour, 15 minutes, but with their comments, I'm able to present this in less than 50 minutes, which is awesome. And yeah, to everybody present, I really appreciate your presence. On Zoom, thank you so much to Dr. Alex for telling me that I was going to China. I had a program in China going to work on, which is a great opportunity. So I had a project in China going to work on pure maths. That was in engineering. And the two are working, but Dr. Alex convinced me that you can go to the US. I thought it's impossible for me because there was a lot to do, but she convinced me to do it. And yeah, I really appreciate. I don't know if my mom joined. She was not there by the time I checked, but I really appreciate commitment to hard work and much he has trained me and my dad as well. Thank you to the faculty, students, and staff in the Department of Maths for teaching us and giving us the knowledge. And finally, thank you to the University of Mississippi Department of Maths for funding my studies and the graduate school for all the help you have accorded to us. With this, I think say thank you to all the attendees of my talk, and I welcome any questions that may. Why? Yeah, we added RAM.
You only consider locally distributed domes.
Yes.
What happens when it's not?
Yeah. Normally we consider uniform.
Yeah, uniform. Sorry.
Yeah, uniform distribution. So if it's not uniform, this is uniform 0, 1. So you realize that there is no parameter there.
Yeah.
It's just uniform 0, 1. To be a different case if it was uniform 0 theta. So definitely the difference is obvious. For example, if we consider exponential theta, if the noise is exponential theta, for instance, we can do more things here, like measure the perturbation in that case. So these are different cases, totally different cases, which I'm considering working on. Yeah. Thank you. That's a very good observation.
Any other questions? I don't have questions because I've been asking questions for 5 years. So if there is no question, then perhaps it's time for the committee members to stay with the candidate.
Thank you so much. Thank you so much for coming.
Very impressive.
Marshall, Nathan Murray. We have not
Oh, okay. Wow.
Yes.
Okay.
A couple of my graduate students, I've tried to get them to.
I think that she has
In turbulence, we have a lot of work with stochastic
I see.
processes.
Mm.
And so,
It's the
we'll
same.
all turn on the meeting, let you guys do your work as a
Yeah.
committee, but.
Thank you, Doc.
I've been in my house once.
Thank you.
Guys,
You know, today.
I have never been there. I'm jealous. I'm jealous. Yeah. We should.
Thank you very much again for coming, all of us today. As the situation,
I have no questions.
comments, and
Question. What about your NLE, humanity, or literature?
I'm not finished.
In your art, the early, you have the humanity of sigma matrix form, right?
Oh, yes.
the MLE.
Uh, your, in your irritation sequence, it is the one for your P, the lesson, huh? Okay.
Because there are different theories.
It's on the 99 page.
Oh, it's the same. I just rewrote it in cases.
Okay, so P
Yeah.
the half, you have negative correlation between your
Oh,
two parameters.
Yeah.
And your formula for your less than half is positive. So how you explain that differences? So you say you have the A times 1 minus P when P less than half for this covariance. And when P greater than half, you have negative AP, that's negative. So one is positive correlated and one is negative correlated.
Yeah.
How you explain the differences? Why it happened over there?
Okay, thank you, Dr. Dan. I would explain that as given that we are generating this is for P less than 1/2.
Mhm.
Let's see. That's the dependence coefficient.
So yeah, the second
What's in the
entry 1, 2, first row, second column
It's the same.
is positive R, yeah, but there's negative P is 1/2. Yes.
Yeah. These
So
are
it's a big jump.
It's intuition how they explain that.
Yeah.
So I believe Marshall will check the mathematical measurements. Just once when you have such a result, you
Not smooth.
need to give us intuitive interpretation of those results.
yeah.
Can I have that copy of the dissertation? Thanks.
I think it's because for P less than
So this here is consistent. If P is 1/2. Because P is 1/2, then the first, I mean, yeah, here 1/2 is 1/2, 1/2 A. The second one is 1/2 A also.
the reason is because this dependence, as we are, comes from M, and M is a we call it a coupler of positive dependence. Yeah. So this part comes from M, coupler of positive dependence, and the M minus P when P is greater or equal to 1/2. This part here comes from W, which is a coupler of negative dependence. That's
But when P equal half, they should be connected as it is two results should agree each other, right?
it's
It is smooth. Yeah, like you said, you don't have that big gap over there. You put
Oh, they
equal
will-
half in the
Yeah, put
second
it
case.
halfway.
Yes.
That is halfway.
It's should be also can be in the first case, right?
That's correct.
Equal
Yes.
half, it can go to the first
Mhm.
case or second case, but right now, if you put into your first case,
Yeah.
that's hold for your second case.
Oh, I see. Yeah, initially we had these being strictly greater than 1/2. But then after a few calculations, we realized that it still works for p greater than or equal to 1/2. I don't remember why we have this, the reason doesn't come.
Is the 1/2 that of diagonal will be 0? In that case, it's fine. You have a separate case, but in here is totally jumped.
Yeah.
Yeah, I just wanted to guess why is positive, why is negative, but right now I think that
Yeah, being at 0.5, yeah. Yes.
Actually, in the dissertation itself, I don't see the proof of that. It is written, we show similar to that.
Equal 1/2 with a special case, maybe, I don't know. Maybe you cannot have a result like this.
When p is equal to
If
1,
P is 1/2, what does that mean?
when p is,
But only 1/2. So
that's the largest variation there.
yeah,
when p is equal to 1/2, yeah,
yeah, 1 or 2.
we will have here
Something will happen.
1 minus a, 1 minus a.
So in
So
order to answer that question, you need to get back to your transition matrices and see what happens when p is equal to 1/2.
yeah, when p is equal to 1/2, we have the case of, we have a here, a, 1 minus a, 1 minus a.
Yeah, this is okay.
Yeah, when p is equal to half, that's what we have. And here as well, we have the same.
Same, yeah, the same. Okay, 1/2, they are
So the-
consistent.
The two transition matrices are the same when p is equal to 1/2.
Yeah, that's why it come to the first formula and the second formula.
Oh,
We agree each other, but
For P.
when it's calculated,
I think so. Yeah, that's good. Good answer, yeah.
Yeah, that's the problem.
That was, some comment on your dissertation paper.
So on page 99, about 2/3 down, it's just a typo. You say we show similarly for p greater than or equal to 2.
Paper, not
I think you
slide,
mean p greater than or equal to 1/2.
Yeah,
right? So
Yeah,
maybe
P level good.
Yeah.
the typo, 1/2.
It's just typo, but
Oh, yes. What page was
Yeah.
that again?
99.
I think, right where I was reading.
Yeah, that's it. Thank you.
Dr. Spinner is eligible to review proposals.
Huh?
Yeah,
What's that?
she's eligible
Eligible to be proposed.
your proposals.
Yeah.
It has a.
Okay,
has
I
to-
believe the right thing to
Yes.
do here is to let him work out these detail, not to say that we're not accepting his dissertation, because I believe there might be a typo there in that answer, because I do not understand. This paper has not yet been published. I do not understand why. And it should switch to a minus sign there.
Yeah,
And the details of the proof I don't see, though they were done. So I can't see where the mistakes. All that is written here is we show similar. And that language I adopted for the paper, not for your dissertation. Your dissertation, you need to provide all the details of the proof that you're claiming.
yeah.
The two proofs.
Okay.
Right now, I can't justify that. It should be negative.
And the other stage is you have the polynomial false order, you want to
Okay.
get the, and I check alpha. They give you a formula. It's complicated, but they give you the formula. And I suggest to you, because you can, you use a numerical solution and they have the formula there, and you provide just what is the exact value, what is your numerical solution. So the formula is very complicated, but you can put in your computer to calculate.
Yeah, but do we really have a general formula for the equations?
I have one.
That's what they claim. But for years, I've known that
It
there's no
is actually well,
close one to follow the equations.
I-
I know they do things like that, but theoretically,
this formula,
you
the
always have
solution of the false polynomial.
What do you mean, do I have it?
This formula is correct or not? I just
Of
check
course,
right
all the
now.
polynomial solution, we have a formula for this one. I think,
It's the quintic that we didn't have, right?
I think the fifth order, no.
Yeah, the fifth order, no, but the quartic is, yeah.
Yeah.
Order, yeah.
Most I think.
Fifth order.
So that's.
the no formula for fifth order.
So that's.
Or above, right? But in general,
Oh, okay.
It's the, yeah.
this is a, fifth is the limit, yes.
Formula and you
I mean,
don't put in your dissertation, but you just say they have the formula there. And you have each of the coefficient, you just
I
put
don't know,
it
maybe,
and
yeah, I
calculate.
think,
That's exactly what you compare with your numerical solution. Everything that with the numerical.
The justification that is given might actually be.
maybe,
that
okay, yeah.
in fact, the W
Yeah, I think we
place
should
where
check.
we switch
Yeah,
We
you
should be, we should be consistent.
one
Yeah.
have less than.
know, now you can. So why?
Not necessarily all to be real.
So, yeah, consistent.
Complete.
Yeah, I know.
They only have two, and they have the real.
What we have is here.
Exactly. I was thinking already
Good catch, I thought.
about this.
Yeah.
Okay, oh.
I got you on that one already. My worry is on this.
But even this is correct.
Oh, I
You
think
have
that
to-
my statement was that there is no condition to agree to guarantee the real solution to that. Before.
Oh, of course.
That's.
Real is no guarantee, of course.
That's-
Even if.
Yeah, that's what I mean. That
Maybe they can have the 1 or 2, it's about it.
Yeah.
It's the formula for the real root for the.
I think the answers they give it in on that mathematical and in complex numbers. So
Yeah, don't provide all the 4 roots, they just provide this formula, I think it's for the real.
So please make sure you go back and check back the reason why these two convergences are different in the limit.
Maybe do some simulation study, to check, maybe they are always positive committee. Do some simulation study, when she figure out.
I do tend to go towards what he's saying, that one part is the positive dependence with M and the other part is the negative dependence with W, because W is when Y equals 1 minus X. So that's perfect negative correlation.
Okay,
So it has to somehow affect that matrix in the end.
yeah,
And
that,
M is the perfect positive dependence when you have Y. That's what
That
most
people
machines
have to.
they
be
switch.
careful, yeah.
The switch, either to be 0 or
Or maybe it's no solution, I
No,
don't know.
the switch is a big
switch.
difference it is a big difference for P equal 1. Because actually the W there is 0. So It's possible that it's not continuous. That one.
Circle there.
Mm.
You cannot be from negative to positive. You have to go through zero. I'm suggest.
That's the thinking, but what I
Yeah, we really show this.
Yeah, special case.
well,
Okay, so what's zero?
Yeah.
Yeah, that's true, Dr. Dan, because we also consider the popular A, 1 minus A, 1 minus A. And the covariance was 0. It's in the dissertation. That is, I think that's what you mean.
Yeah, you need to check. You need to.
Yeah.
Equal one half.
right on those steps.
Formulas and pick one half to go there.
Yeah.
Because even those two are correct, you still have problem when people's half.
Yeah, and then what I'm saying is, it's quite possible in this case that
Mhm.
there is a
Yeah.
jump,
Yes.
that there is
Yeah.
a jump.
Yeah,
One
yes.
half has to be one of
Right.
them, but
Yeah.
the jump is also possible.
I'll be right back. I have to,
But
step out.
one half has to be included in one.
But the translation form exactly the half can be go to this way and that way should be to be one of those. Or yeah, so I think the people have must be some other value to make them they have the 3 jobs instead of 2 jobs.
If you go back, can you go back to your matrices again? Original. So when P equals 1 half, what's the matrix A? That you write down on the board was. Both matrices.
Goldman.
Here, one half is this, yes.
Okay, and because P is 1 half, what's the probability?
Thank you.
Probability that x1 equals 1. Can you compute the probability that x1
Are we
equals
still
1?
on the same issue?
I was, huh?
Are we still discussing?
Oh, yeah, this is, yes.
Probability that x1 equals 1 using that matrix. And the transition matrix, no?
Yeah,
How do you compute probabilities using the transition matrix?
I used that.
Multiply on the left by the distribution.
Probability.
Oh. Oh, goodness gracious. What they get. Oh, yeah.
Joint. The joint matrix that you have, I wanted to show to you to write down the joint probability that x0 equal 1 and x1 equal 1 using your matrices. You have the joint matrix somewhere there. You can roll it back and look at that matrix, see what the answer is.
Probability x1 equals 1.
What is it in this case?
So, oh,
Probability that x0 equal 1 and x1 equal 1, what is it equal to in this case?
probability x1 equal to 1. It's stationary. statistical.
I'm asking you for the joint probability, x0 equal 1 and x1 equal 1, or isn't?
Okay,
AP, if P is 1/2, that's A over 2. In the other case, what is it? Is it the same thing? When you're using the table for P greater than 1/2. I'm trying to figure what's going on with the matrices and where it goes.
it's different, it's different.
Can you go to the other table?
It's not presented. And it's in statistical.
Are these tables in this dissertation?
Yes, the,
What-
Look at page 84,
Okay.
85. Where P equal 1/2, there it's also 1/2.
Yeah.
It's also A over 2. So the problem is not in your joint distribution, with the joint distribution are the same in the two cases, and definitely they should coincide. When
Mhm.
they should coincide, that's why I was checking what we were discussing. So there should be a typo in your proof. Because if the joint distributions in the two cases were different,
Different, they may have the
then
different,
they might have
the
different
limited
limits.
distribution.
Yes.
So, I'm curious, if I want to apply the method, to detect if there's any, dependencies, due to the perturbation in the model, how do I do that?
Test, test dependence in due to the perturbations.
So without the out of this conflict, that's what the next student is working on. Yeah, taking specific functions, specific alpha and the functions field, and starting taking finding estimators for that alpha and giving the limit theorems with it, giving ideas of how to test and so on. He didn't put anything related to that. That's what Muslim who went say.
So the way I think of noise, and you can correct me if I'm wrong here, but noise is like maybe bad data or something? Is that correct? Well, so I wanted to ask, what's the difference between noise and perturbation?
So let me go back here. In that. Let me explain the first perturbation. They are connected. So in this case, or in this perturbation, considering this case, we are bringing in a new a population with a copula C1, contaminate the copula C.
Okay,
So we are contaminating the copula C with another copula from a population with copula C1. And that can be classified as noise as well. Yeah, it's like affecting the previous data using data from different populations.
okay,
An easy way to think of it is you have your data, large data, and it's stored somewhere where there is something else that is affecting part of the data. The affected part of the data has a slightly different distribution. Therefore, when you're picking an observation from there, you have a chance that it comes from the one that has not been expected, or it comes from the one that hasn't. That's the probability alpha and 1 minus alpha.
Okay. Thank you. And can you go to slide 38? I mean, none of my questions are gonna be that deep because you've got the statisticians here to pick this whole apart. But why are all the parameters that you chose tenths of, you know, like 1/10, 3/10, 4/10? Why not like 0.487?
Yeah, that's correct. We can consider those ones, but then we will have an infinite choice. So we just chose to go with the 1 decimal place choices. And here we only chose A 0.1, 0.2, and 0.7, and B 0.1, 0.3, and 0.4 to avoid a very large table. And also, we can choose A to be 0.1, 2, 3, 4, but then we'll end up with having to do a lot of tests. It's unlimited. What we wanted to observe is the estimations.
The point you also is to showcase the one how thing we are discussing here now, how it affects, how that one how affects the tables.
So what's the restriction on A?
In our case,
Probability. So why don't you choose something close to 1/2?
A is from 0 to 1, and if you see like A close to B, you have a difference.
Equal to P. Okay.
So instead of independent, it's A equal B.
Okay.
But you could run this, you could do this table again, right? For P equals point, like I said, 0.4873, blah, 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 and then P, I'm not asking you to do this, and then P is equal to 0.512, blah, 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 right? And keep the same A and
so that means if the true value of P is, for instance, 0.512, I'm generating the Markov chain with because yeah, with P is equal to that value. So I will generate a Markov chain such that the probability of success in the Markov chain is 0.512. So the estimation will still take me close to 0.512, something close to that. 0.50, 0.514. Yeah, I think it can be more accurate, probably, if I use that. I think the accuracy will improve by considering all the small points.
You use R, right? For simulation study,
Yes, sir.
for which package to generate your Markov chain? What's the package you mentioned?
No, it doesn't use the fact. That's the point.
You write the whole
I
code?
just wrote
It
the
is on code.
Okay, so that, okay, in that case, so how can you guarantee you have some property, right? Yeah, I mean, some condition on your Markov chain from your theorem. So how can you guarantee the condition? I mean, yeah, I believe you check it, like with short, the generated data satisfy the condition.
Generated from the exact distributions that I used.
Okay.
Yeah, since we have
So when you're using the calculus and you have a closed form to the calculus, it's not an estimation procedure. So your xi, x1, x2, x3 exactly from the distribution. It's not estimated.
Okay. So, okay, also maybe if you have your own R code, maybe you can develop a package. I don't know.
I asked them all to try that, but nobody is trying. I don't know how to do that if they want. you can do that.
Yeah, I didn't think of doing that, but
But why not put the code
Well, they
in
have a lot.
the dissertation? I think it's,
Is it not?
yeah, I talked to Dr. Long about that. I will include before I submit it to the grant.
That is not in there.
I will include.
You want to keep a secret?
Because
Well, then
I
you have to
actually
publish.
proposed, to them
People can
to
use
write
it.
a paper.
You have
because
to-
there are journals that actually publish codes, that
Right.
just write a paper on all the codes that they are doing, because it's all on the same topic. And make a package out of that, submit that, but.
Yeah, you can make a package, publish.
They're not doing it, so.
People can use it.
I'm not doing it. The good thing about this is that the formulas that they are using are general. So you just write a formula, write a formula, P, so that anybody can just bring his own functions and put in it and just have the answer. That would be a result, but it needs to be done. Right. All right, anything else with him? So, or we can release him because requesting 15.
yeah, I wanted to go to that vice chancellor, presentation. Oh,
Oh,
that's informative.
it's interview, right?
Yeah.
All right, so we can release you
Yeah.
and you wait outside.
Yeah, for a couple of minutes.
We release this online too.
People online, we can stop them
Okay, okay.
or just
That's
mute.
Yeah, let's mute because I don't know that they should hear our
Yeah.
discussion.
Just mute them.